In Professor Carlos Frank's remark, "I've spent my life at Durham University, my entire life forming a particular perspective on the world, and that concept is currently being questioned. Because it is, I welcome it. This is how science advances." James Webb is reversing almost all of what was known to be true in cosmology for the past century. A new ultra-deep image depicts the progress we've made, and the errors in astronomy. The telescope was supposed to demonstrate the initial stars of the universe's past, but instead, that past is being destroyed by a new perspective. This may usher in a new science. Many researchers are not afraid at all. Researchers impacted by the new developments welcome the information, because it's been clear for a long time that there was a problem with our previous hypotheses, contradictions in determining the expansion rate of the universe. These contradictions should have awakened academics earlier, rather than causing them to misinterpret clues and cling to outdated notions. The cosmic microwave background radiation, CMBR, is thought to be the universe's oldest light. The CMBR was formed around 380,000 years after the Big Bang, when the universe had cooled to a point where stable connections between protons and electrons could form, hydrogen atoms, as researchers describe them. This transformation, such as ionization, made it possible for light to travel freely through the universe. American scientists Robert Wilson and Arno Penzias discovered the CMBR in 1964 while working on a new kind of antenna. They heard a constant noise approaching from the sky in every direction. This discovery was widely accepted as one of the most compelling pieces of evidence supporting the Big Bang theory. Penzias and Wilson shared the Nobel Prize and made history in astrophysics. The CMB most likely provides us with a glimpse of the young universe. Tiny temperature changes provide significant details about the conditions in the universe shortly after the Big Bang. Scientists have measured the universe's expansion rate and other factors using the CMB, factors that astronomer Edwin Hubble had already begun computing in the late 1920s. Hubble discovered that distant galaxies move away from us in all directions at speeds proportional to their distance. Today, we refer to these measurements as part of the Hubble law. Naturally, Hubble did not use the Hubble constant, nor did he possess the advanced measurement methods we have today. Decades later, when the CMB was discovered, researchers recalculated the rate, and the new number was significantly less than Hubble's initial estimate. Subsequent research further refined the rate using type Ia supernovae. Like regular candles, these provide a dependable point of measurement. The disparity in determining the universe's expansion rate has existed since the 1990s. Researchers have been aware, or at least suspected, that there was a problem with our evaluation methods or with the very idea of an expanding universe. This issue, known as Hubble tension, refers to the difference in measurement of the universe's expansion rate between various methods. It has far-reaching repercussions beyond a simple measurement error. Numerous discoveries now reveal that our previous understanding of the universe may have been fundamentally flawed. The James Webb Space Telescope has provided scientists with unexpected results that may offer insight into the expansion rate problem. It has revealed extremely old and mature galaxies that, by current theories, must have existed before the Big Bang. This completely opposes traditional science and astrophysics. There is no longer just talk of measurement. Academics are now discussing the most significant issue in modern astronomy. Not only might the universe's expansion rate be wrong, but the entire concept of expansion, or even the Big Bang itself, is being tested. Webb's photos reveal a universe very different from what we believed for a long time. The tension served as an early warning, and now, theories once held as truths are being put to the test. Do we actually know anything about the universe? Many scientists are now standing amid the wreckage of their life's work, staring into space, uncertain of what they are seeing. Given the current scientific dilemma, we must ask, what do we truly understand about the universe? To address this, we must first comprehend how science works. Theoretical scientists use a complex network of mathematical representations of actual data and deductive reasoning to reach conclusions, from general to specific. Their expertise is based on a combination of observed events, extensive experimental data, and theoretical analysis. This alone shows that we deal in concepts, not necessarily reality. Practical knowledge comes from telescope images, sounds, radio waves, and data from measurement systems or gravitational wave detectors. With the James Webb Space Telescope, we now have an instrument capable of breaking down earlier ideas into distinct frequencies and analyzing them in ways never before possible. Webb can show us which elements were present in galaxies over 13 billion years ago, how much mass they had and how many stars existed. It can reconstruct a galaxy's shape and direction of travel. But even Webb has limitations. Due to massive accumulation disks, it sometimes cannot distinguish whether we're seeing black holes or galaxies that shine as brightly. We must confront the long history of science accepting too many outcomes as realities, while ignoring alternative explanations. Research has long assumed it was correct. However, the most recent information from Webb offers important clues, replacing old ideas with new facts, as has happened many times in science. Researchers now await further data. The outcomes are far too strange, and it's nearly impossible for many to offer coherent interpretations. These new discoveries challenge the very fundamentals of modern physics. This scares many scientists. Today's physics classes are still based on 17th-century discoveries by Isaac Newton. For over a century and a half, his principles of motion and gravity served as the cornerstone of our understanding of the physical universe. His theories explained motion under normal conditions and worked well on Earth, but in space, they needed to be expanded. Albert Einstein did this in the early 20th century. His special theory of relativity, 1905, transformed our view of space and time, showing they are interconnected and relative to the observer's motion. He expanded this into his general theory of relativity, 1915, mathematically demonstrating that gravitational phenomena result from space-time curvature caused by massive objects. Einstein's theories were cohesive, but he knew their limitations. He believed they would never be enough to describe the entire cosmos, and he hoped to find the ultimate formula, but he never succeeded. Interestingly, no one else has either. Where is the mistake? Wouldn't it be fascinating to find out? Michio Kaku, a well-known US physicist, once said in an interview, "The individual who overcomes this obstacle will undoubtedly win the Nobel Prize." Scientists must now examine the facts and ask, where have they ignored signs? Where have they misunderstood events? Perhaps it's dark energy and dark matter that are to blame. Our current theories suggest that dark matter and dark energy together make up about 95% of the universe's composition. However, despite their supposed dominance, they remain elusive. Vital information that bridges the gap between the quantum realm and the cosmic scale. The anomalies observed by the James Webb Space Telescope may not be mere observational quirks, they could be signposts pointing us toward a unified theory of everything, the long-sought goal that has eluded physicists for over a century. If our models are flawed, then perhaps we must question the very scaffolding upon which modern cosmology has been built. The implications are not only scientific but also philosophical. What is time, truly? What is space? Are we even capable of grasping the full nature of reality, or are we forever limited by the lenses, mathematical and literal, through which we observe the universe? The JWST's ultra-deep field images are showing galaxies too massive, too evolved, and too structured to fit into the early timeline prescribed by the standard model of cosmology. In short, we are seeing things we should not be seeing, at least, not so soon after the supposed origin of the universe. This temporal contradiction has shaken the scientific community, forcing many to reconsider the validity of the lambda-CDM model, which has long served as the prevailing cosmological framework. The consequences are vast. If the formation of galaxies began earlier than expected, then the mechanisms of structure formation must also be different, possibly faster, more efficient, or governed by laws we have not yet uncovered. And if the Big Bang theory itself is incomplete or incorrect, then the very question of the universe's origin reopens in full. Some propose conformal cyclic cosmology, where the universe undergoes infinite cycles of death and rebirth. Others suggest quantum bounce models, where a previous universe collapsed before giving rise to ours. Then there are theories invoking the multiverse, where our universe is but one of countless others, each with its own physics, its own beginning, and perhaps, its own version of life. But we must proceed carefully. Scientific revolutions are not born of speculation alone, they are earned through rigorous data, replicated results, and theoretical elegance. The JWST offers us unprecedented clarity, but it also burdens us with responsibility. We must decipher the truth hidden within these alien lights, not just to advance our understanding, but to recalibrate our assumptions about everything from time and gravity to matter and causality. In the face of all this, many scientists find themselves at a crossroads, cling to familiar equations or venture into the unknown. Perhaps, as Carl Sagan once said, somewhere, something incredible is waiting to be known. And perhaps that something is waiting in the silent, ancient light now reaching us from the edges of time itself. Towards solving this enigma, but where do we begin? Here, the scientific method demands that we test new hypotheses, expand advanced tools, and remain receptive to fundamental shifts. The future is just the beginning of the JWST. Telescopes and experiments will continue to improve our comprehension of the cosmos. It's conceivable that, in the upcoming few decades, we may witness a complete reorientation of our perception of the universe, just as Einstein's work revolutionized physics in the early 20th century. The discovery is a long way off, and the most significant revelations could still await the universe. Despite the fact that it has never been directly witnessed, indicating its actual existence, neither have they established that it does not exist. We must demonstrate the galaxy dynamics and the expansion of the universe, either alone or together, possess characteristics we do not yet understand. One theory now being discussed is that the physical properties of the two dark components have evolved over time, which lets us know that we are dealing with something that is the next thing after intelligence. The type to be tested is gravity. This force, which presumably draws people in or curves spacetime due to mass, has yet to be demonstrated. Einstein is a significant contributor to the concept of space's curvature and time, which has been repeatedly proven correct. However, we cannot exclude the chance that gravity has completely different characteristics than previously thought, or that the force of gravity is a different factor that separates objects. The mechanism of several cosmic values has established constants in modern cosmology and astrophysics. The number of years these values have been dependable is because they rarely alter. Calculations have revealed that slight changes in the so-called constants create new momentum throughout the universe, allowing us to explain a variety of events that do not include dark energy. It could also be that our interpretations of the redshift of light are erroneous and that we have been measuring incorrect distances of galaxies that determine the universe's age. Perhaps our beliefs regarding the universe's origin were likewise erroneous. We may have misinterpreted the background of cosmic microwave radiation. It's also possible that the universe has no beginning or end. This would apply to a single point of beginning and imply that the Big Bang theory is incorrect. Despite our sophisticated technology, we cannot rule out any small errors in the Webb telescope or other observational instruments. In the midst of this crisis, scientists and engineers agree that errors in interpretation and processing of data are critical. Cosmology is always open to new ideas and possibilities. At the moment, it is at an intersection where the foundations, laid over the course of centuries, are being tested by new information and observations from innovative equipment like the James Webb Space Telescope. This does more than just raise difficulties, it raises concerns regarding well-established theories, but also opens new opportunities for comprehension of the cosmos. It's one of the fundamental principles of contemporary cosmology, the Big Bang, which asserts that the universe began at a point where it was infinitely dense and has been expanding since. This theory has been backed up by a variety of lines of evidence, such as the cosmic microwave background, CMB, Hubble constant, background radiation measurements, and the distribution of galaxies across the cosmos. The discovery in 1964 was a pivotal moment in cosmology. It offered substantial evidence for the Big Bang theory by showing a uniform glow of radiation across the horizon, which is thought to be the hot afterglow of a dense universe in its earliest state, before it became transparent enough to be seen. This radiation has since been studied extensively to understand the composition, age, and geometry of the universe. Despite recent findings and measurements, particularly from the JWST, significant challenges have been introduced. The JWST adheres to this established framework, but with an unparalleled level of sensitivity and resolution, it has started to unveil phenomena and galaxies that defy typical explanations. For example, the finding of galaxies that seem to be older than expected raises fundamental concerns regarding the timeline of cosmic evolution and the processes resulting in the birth of stars and galaxies. Moreover, discrepancies in the measurement of the expansion of the universe rate, known as Hubble tension, remain, despite decades of advancement in observation techniques. While the CMB-based measurements indicate a specific rate of growth, independently measured outcomes from Type Ia supernovae as standard candles give varying results. This discrepancy hints at potential flaws in our understanding of either cosmic distances, dark energy driving the universe's acceleration, or both. Energy remains an unidentified component of the vastness of the universe, making up the majority of its material, but defying direct detection. These mysterious substances are invoked to explain the observed gravitational effects on the accelerated growth of galaxies and the universe itself. However, their specific properties in nature continue to elude scientists, leading to various theoretical and experimental efforts to uncover their identities. In addition to these difficulties in theory, the JWST has provided visually stunning phenomena that call into question our current knowledge of the history of the universe. Images of faraway galaxies, including some that existed just a few 100 million years after the Big Bang, suggest a complicated and early universe with rapid change that may require new theoretical frameworks to comprehend. The JWST's primary capacity to examine the light spectra produced by these ancient galaxies reveals their compositional chemistry, star formation rates, and the very existence of important, bulky components required for the formation of planets and life. These observations not only improve our comprehension of the formation of galaxies but also raise intriguing questions regarding the circumstances under which life could emerge in the universe. Furthermore, the idea of cosmic inflation, which posits a rapid and exponential growth of the universe immediately following the Big Bang, remains a subject of discussion and scrutiny. While inflationary models provide sophisticated explanations for the observed structure at a large scale of the universe and the CMB's uniformity, alternative theories that do not require inflation are actively pursued to reconcile inconsistencies in theories and observational challenges. This ongoing quest to understand the cosmos raises profound questions about our place in the universe. As technology advances and the JWST provides even more detailed images and data, we may find ourselves questioning not only the history of the universe but also our assumptions about the fundamental nature of reality. The universe could be far more complex and interconnected than we currently imagine. The possibility of a multiverse, for instance, challenges our understanding of existence and raises metaphysical questions that could reshape both scientific and philosophical thought. As we push the boundaries of exploration with advanced telescopes and observatories, new discoveries could prompt revolutionary changes in our understanding of the universe's structure, its origins, and its ultimate fate. The vastness of space, coupled with the mysteries of dark matter and dark energy, suggests that we are only scratching the surface of a far greater cosmic reality. Each breakthrough, whether it's uncovering a galaxy older than expected or refining our measurements of cosmic expansion, brings us closer to a deeper, more nuanced understanding. Theories about the universe's beginnings, such as the Big Bang or alternative models like the steady-state theory, are constantly being tested, refined, and sometimes appended. Our understanding of time, space, and the very nature of existence continues to evolve, influenced by discoveries from instruments like the JWST. As we gather more data, it may lead to a paradigm shift that redefines the fundamental laws of physics. The relationship between the observable universe and the unobservable realms of dark matter, dark energy, and potential multiverse may soon be understood in ways we can barely fathom. The future of cosmology lies not just in new telescopes or technologies, but in a willingness to ask deeper, more profound questions, questions that challenge our understanding of reality itself. The exploration of distant galaxies, the study of cosmic background radiation, and the measurement of the universe's expansion all serve as stepping stones toward answering these questions. What we uncover next could change the very course of science, philosophy, and perhaps our entire worldview. As we look to the future, the JWST and other next-generation instruments will continue to guide us through this uncharted territory. The universe, with all its complexity and mystery, offers us a vast, ongoing puzzle that humankind is only beginning to piece together. Each discovery adds a new layer to our understanding, revealing a universe that is far richer and more intricate than we ever imagined.